So are we good to start?
So our next talk is again by our own Ioannis Soranidis, and also about black hole, a little bit of information, and all the rest of the interesting stuff.
Good morning, everyone. Thanks, Danny, for the introduction. So today I'm going to talk about implications of singularity regularization in black hole thermodynamics. And this talk is going to be based on the following three papers. The first one is in collaboration with Sebastian Merck from Okinawa Institute of Science and Technology in Japan. Second one with Phil Simowitz from Macquarie University. And the last one is by myself. So quantum gravity has been a long-standing quest, although with limited success thus far, and we expect that if such theory exists in nature, it will describe it at a reasonable accuracy, and singularities will not occur, and paradoxes such as the infamous black hole information paradox should not arise. But in the absence of such a comprehensive theory of quantum gravity, it would be useful to study effectively its properties and see if we can get some insight on how to proceed. And to do that, we need to find appropriate laboratories to perform these studies. And these should be regions of space-time that admit strong gravitational fields. Without any reasonable doubt, we know that such objects exist in our nature and are ultra-compact objects, and they can neither have the property of horizon or not. If they don't, they are horizonless configurations. If they have the property of a horizon and under the quantum gravity theory assumption, we can have singularity, so they are regular black holes. A full classification of objects with horizon can be found in the review paper here by Mann, Mark, and Turner. And today I'm going to focus on the regular black hole case. So one reasonable question is, how do we source these geometries in the context that we have the tools to study them? So one of the ways is to have nonlinear electrodynamic theories and couple them to general relativity. So NED theories have been successful in the past eliminating singularities associated with the electric charge, such as Bohr-Infill theory. Apparently they can do the same for gravitational singularities, but only at the cost of introducing a magnetic charge, which has not been observed in nature thus far. We expect, as the Bohr-Infill theory was replaced by quantum electrodynamics, a fundamental theory like quantum gravity will replace this effective way of generating these geometries. Another way to generate these geometries is by using Gauss-Bonnet corrections to the Einstein-Hilbert action. And in order to have non-trivial contributions from this correction, we need to add a scalar field in 4 dimensions. And last but not least, look, quantum gravity can also generate regular geometries. But today I'm going to focus on the first case where we have general relativity coupled to NED, and I'm going to restrict even further in the case that we don't have any electric charge and we have spherically symmetric cases. So under these assumptions, we have a 4 potential that has this particular form and depends only on the magnetic charge Qm. And the action of such a theory is given by this form, where R is basically the scalar of space-time, lambda is the cosmological constant if present, and L of F is the NED Lagrangian density, where F is the field strength and it's calculated by the contraction of the electromagnetic field tensor. And in this case we're studying, we can calculate that it depends on the magnetic charge and the radial distance R. There are NED theories that depends on the dual scalar as well, but I will not talk about them today since NED Lagrangians that depend only on the field strength are sufficient to generate geometries that I'm going to study today. So, as I said, we will study spherical symmetric cases, so we will have a line element of this form, where f of r will be the metric function. And in order to demonstrate some of the thermodynamic properties in the second part of my talk, I'm going to use 3 specific regular black hole models that I'm going to introduce now. So the first model is the Hayward model. As we can see, the metric function depends on 2 parameters. We have m, which represents the Komr mass of the spacetime, and we have a minimal length scale L introduced to regularize the spacetime. We can see that when L goes to 0, immediately we retrieve the Schwarzschild metric, which is singular at the center. And to generate such geometry, one has to use an NAD Lagrangian of this form that depends on an extra parameter alpha and the field strength F that we saw that depends on the magnetic charge previously. So this NAD Lagrangian generates a geometry that has A, alpha, and Qm, and we can identify these parameters so we can generate the Hayward model. A rather unpleasant feature of this geometry is that the weak field limit is not the Maxwell limit, but it's stronger than that. And this is rather unpleasant because we know that Maxwell theory is a well-established theory. And another feature that we should pay attention to is that the magnetic charge also depends on the Kommer mass here. Second geometry I'm going to study is the Bardeen model, which is actually the first model that was proposed in the literature. It shares similar features as the Hayward model. We have a Kommer mass n and we have a minimal length scale L to regularize the spacetime. We have an NAD Lagrangian. Again, we can identify alpha and Qm to generate this geometry. And we have, again, that the weak field limit is stronger than the Maxwell. Since these two models have this feature of having weak limits stronger than the Maxwell, I'm going to focus on the third model for demonstrating basic thermodynamic properties, which is a model that was proposed recently in the literature by Gadoni and his collaborators, I think 2022. So this model has this metric function, similar features as the other ones, but now we have a weak field limit that is the Maxwell limit. And this property is why I'm choosing this model. In all of the cases, as we see, the magnetic charge depends on the Kommer mass n.
So what does that mean? Like, it means like sourced by matter?
So the magnetic charge is an artificial way of generating these geometries, and the dependence of in the Kommer mass on the Kommer mass will affect the first law later, and will create some extra terms that will correct the temperature. So I'll talk about this in a bit. So since I've introduced some motivation on why we should study regular black holes and we saw how to generate these geometries, I'm going to proceed now with the study of thermodynamics. So to properly study thermodynamics, one needs to first calculate properly the thermodynamic quantities. We can use Hamiltonian formalism or we can use Euclidean path integral formalism. Both these lead to congruent thermodynamic quantities. This is something that we proved with Phil in this paper, and basically we use the Hayward model to demonstrate this consistency between these two methods. And the first thing we are doing when we have thermodynamic quantities is to see what is the form of the first law. So E here will represent the internal energy of the system, and it will be played in these models I said before by the Kommer mass. T will be the temperature, S the entropy, phi will be the conjugate potential to the minimal length scale L, which is treated as a thermodynamic variable here, and the thermodynamic volume will be the conjugate potential to the pressure, which arises by the presence of a cosmological constant. In the case of a de Sitter space-time, this is interpreted as a tension. So what we find by these two methods to obtain the thermodynamic quantities is that we have a temperature which is proportional to the surface gravity, and we have some correction terms which come from the minimal length scale L. We can calculate the potential for the thermodynamic variable lambda, and the thermodynamic volume, which is basically the usual geometric volume of a sphere, but with a correction factor. So the entropy is calculated directly from the Euclidean path integral, and it's the Bekenstein-Hawking entropy. So some comments before we proceed are why we treat the minimal length scale and the cosmological constant as thermodynamic variables. So we expect to have more fundamental theories, and we expect the minimal length and the cosmological constant to arise from vacuum expectation values of fields. As for the minimal length case, we've seen in the literature that when back reaction is accounted for, we can have varying minimal length scale. So as we'll see later on, this is not the Planck scale, it's connected to this, but it has larger value than this and it allows to vary. Also, we see that all the couplings that appeared in the NED theories, the alpha factors we saw previously, they were dependent on L, and we've seen that in the study of thermodynamics that we had variations of coupling constant like Gauss-Bonnet theories. But the more practical reason that we can find is that without treating L and lambda as parameters, the smart formula will not be satisfied. Second thing is, why do we have a modified temperature, and if we can trust this theory to produce the thermodynamic variables? So, in general, when we derive the Hawking radiation temperature, this whole derivation is heavily based on the kinematic features of this geometry. So we have that photons and gravitons moving on null geodesics. But if this is not the case, we might have some modified temperature. So this was first shown in this paper by Liberati and the rest of the people, where in Horndeski theories of gravity, which are the most general theories you can have in 4 dimensions that admit second-order differential equations of motion, they find that when we have the modified graviton velocity, then we have some modified temperature. And we saw that for this Keller-Einstein Gauss-Bonnet can also generate regular black hole geometries, and we can always find transformations to map this theory to a Horndeski theory. And when we do that, we have in the Horndeski-Lagrangian terms that have the Einstein tensor coupled to covariant derivatives of the field. When this happens, we have some modified temperature. But this reasoning was proposed in this paper by Liska, Henniger, and Kubisnak, where they were studying singular geometry. But here we are studying a regular geometry, and we can make a connection between the field and this modified temperature.
Sorry, how do you find the speed of graviton?
So there is a specific way to find the speed of graviton in Horndeski theories, that you compare the G4 and G5 terms in the Lagrangian. So I don't remember the exact derivation of that now, but the way that you can derive that is connected to the fields that you have.
Yeah, but the normal definition of graviton on a flat space
it's gravitational perturbation, and they calculate this. But the problem is that all geometries that we've seen, regular or singular, when we have these fields, they either diverge on the horizon or the first derivatives diverge on the horizon, and this creates problem in calculating the graviton velocity. So there's no way to say that there is consistency between the temperature we derived here and the graviton field. But this is something in the geometry. Yeah. So since we have the thermodynamic quantities, one can calculate the free energy and start studying phase transitions. So here the phase structure is studied in the case of ADS spacetime, because phase structure is mostly understood in this case. And we also restrict to the canonical ensemble, where we fix the magnetic charge. So once we combine the thermodynamic quantities, we have an equation of state that has this particular form, where it's a van der Waals-like equation of state, where the denominator here represents the reduced volume. So in the usual van der Waals studies, this represents the volume over the number of particles. And usually in the literature, when we study phase transition, what we use as reduced volume is the 2Ra's quantity. But here we see a correction term coming from the minimal length. So as for the phase structure, so we can focus on the blue curve. So on the left diagram, we have varying minimal length scale, and on the right, varying cosmological constant. We see similar features in the phase structure. So the arrows indicate the direction of increasing horizon radius. So let's say if we start with some small temperature here, and we have a mechanism of increasing the temperature, and we will reach a crossing point, and at this crossing point, the system will choose to minimize the free energy, so it will move downwards. So from a small black hole, we go to a large black hole, and this is a first-order phase transition. So we see that the Hawking phase transition is absent in this case. And this is inherently linked to the presence of a minimal length scale, L. So taking the crossing points here, and combining all of them, we get a coexistence line, and this line will terminate at the black dots, which represent critical points, and these critical points are second-order phase transitions. And when we have critical points, one usually studies the behavior of thermodynamic quantities near this critical point and compares them to the mean field theory. So we have 4 exponents. The first one, every behavior is being studied with the reduced temperature. So the reduced temperature is defined the deviation of the critical temperature. And for the heat capacity, it scales with the exponent alpha. And we find that the heat capacity is independent of the temperature, and we can identify alpha being 0. The second exponent is a bit more tricky to find because it's very difficult to solve analytically because this requires to find the reduced volume for large and small black holes at the coexistence point, and to do that we need to solve 5th order equations. So instead of that, we feed numerically here, and we see that the blue dots that represent the difference of this volume scale exactly as beta being 1/2. The isothermal compressibility scales with the coefficient with the exponent gamma. We can find this analytically going through the horizon radius. We find that gamma is 1. And as for the difference between the pressure and the critical pressure with respect to the difference between the volume and the critical volume, we find that delta is 3, and these are the usual mean field theory exponents. What is interesting though is that despite the fact that we have these critical exponents being the same as the mean field theory, we have a deviation for the mean field theory critical ratio. So usually in the mean field theory, we have a critical ratio which is calculated by a combination of the critical pressure, the reduced volume, and the temperature, and we find that it's 3/8. So these 3 models admit different corrections to the asymptotic behavior, and this is inherently linked to the way we choose to smooth the singularity. So for the Hayward model, we see corrections of order r to the -4, which are weak corrections. Bardeen has slightly stronger, and the strongest one are exhibited by the Catoni model, which is r squared. We see that the mean field theory ratio deviation gets larger as the deformations from the geometry become larger. So the way we choose to regularize the singularity has some effect on the deviation from the mean field theory ratio, while the critical exponents for all these 3 models remain the same as the ones in mean field theory. And some comments here about the minimal length scale L and how we can actually observe that. So in this paper by Catoni in 2022, when they presented the model I've used today, they found that we can have deviations from the perihelion angle and that scale linearly with L, so they can make some observations and constrain L and see if they can actually match, and we can actually have regular black holes as a possible alternative for ultracompact objects. So here I'm going to use the assumption that we have a small cosmological constant, and I'm going to extract the thermodynamic quantities in Minkowski and use them to impose some bounds on this minimal length scale L with the mass of the object. So usually for any regular black hole model, we have this specific form where for some values of the minimal length scale L, we can have 2 roots, and these 2 roots will represent the inner and outer horizons. There is always a critical length which makes these 2 roots to coincide, and we have a double root, and this indicates that we have an extremal black hole. And after a certain point of the minimal length scale, we don't have any roots anymore, so the geometry now describes a horizonless configuration. So if we say that we want the object that we observe in nature to be regular black holes, that means the existence of a trapped region. So a lower bound is imposed by the requirement that these should be present and not horizonless configurations. So we have a bound, a lower bound that comes from the extremal limit. And one more bound can be imposed by the thermodynamic stability. So if we want the objects to be thermodynamically stable, then we need to have a positive heat capacity, and there is a specific point that we have a change in the sign of the heat capacity. So this imposes an upper bound for this, and we can see that the value of L will be huge since the mass of black holes is huge. So we see that the minimal length scale is not the Planck scale, but it can be larger than.
And sorry,
yeah.
By stable you mean this is a long-lived or stationary object, so it's like a big remnant, so it's not like a black hole that is has negative heat capacity but evaporates.
Yeah, here we assume evaporation.
Okay, so what is the definition of stability then?
Positive heat capacity.
Okay.
What do you mean? Maybe I don't understand.
No. What bothers me is most of gravitational systems have negative heat capacity. Black holes have negative heat capacity. So,
but they don't always have negative heat capacity. It depends on what parameters we have in the theory. For example, when you introduce cosmological constant.
Okay. Yeah. Cosmological constant changes the rule.
Yeah.
Yes.
Okay,
I had the simple reflection.
Here, the extra parameter that we have is L, and this is what changes this behavior here. If this was not the case, then yeah. Okay. And everything I've done up to this point is static, and now we'll proceed to dynamical cases. So in dynamical cases, dynamical spacetimes, we know that we don't have time translation symmetry. So we don't have a killing vector. But instead of that, as Pravin explained in his talk, we have a Kodama vector, and we can use the Kodama vector to extract some associated charge. The conserved charge is the Misner-Sharp mass here. And to indicate now the time dependence, we are using the advanced coordinate V. So now the metric function is given in this particular form, where C/2 will be the Misner-Sharp mass. And we can always find a near horizon expansion of this function, where R plus now is the horizon radius, and W1 is a linear coefficient of this expansion. So as we will see, W1 will be sufficient to demonstrate all the thermodynamic properties of dynamical regular black holes. So we showed with Sebastian that W1 is different than 0 in every regular black hole model. And as we will see in the following slide, this is inherently linked to the presence of a minimal length scale L, or if you want, the absence of a singularity. So in this case, the first law is given by this particular form, where now we have two differences with the static case. First one is that the internal energy is not played by the Komar mass, but is played by the Misner-Sharp mass evaluated on the horizon. And the second difference is that extra terms associated with a minimal length scale L are not showing up as the conjugate potential phi, but they show up as pressure terms in the first law. The temperature is given by the Kodama surface gravity here, and this is a result of choosing the Misner-Sharp mass as being the internal energy of the system. So to show some specific results, some specific examples, for the Hayward model, W1 of V has this form. For the Bardeen, we have this, and for the Cadoni model, we have this. As we see, in all cases, when the minimal length scale will vanish, we will have W1 being 0, no pressure terms, no contributions because of the minimal length scale L. And I will summarize now. So the absence of singularity may suggest a couple of things. We might or might not have a modified temperature. This derivation might depend on the theory we choose. So this kind of geometry should be studied further. We don't have a Hawking phase transition, and this is reminiscent of what is happening in the Reissner-Nostrom case when we fix the electric charge and we don't allow the black hole to evaporate completely. Same thing is happening here, but we fix the magnetic charge, and this fixing the magnetic charge means that we have a minimal length scale L present. We saw that the way we choose to regularize the singularity leads to a deviation of the mean to theory ratio, and The extent of this deviation is based on how strong the deformations are from the geometry. And the last thing we saw is that we have difference between the static and the dynamical laws. Quantities are interpreted in a different way, and extra correction terms are introduced in different ways. And I will stop here. Thank you.
Oh, actually, very well regarding the time. So, questions, comments, we can even have a little. Yeah, yes, sir.
Ask a question for clarification. Actually, so this parameter of minimal length, it emerges from the nonlinear theory of electrodynamics. That part of the Lagrangian, or?
So here we will get the geometry from these equations of motion. We solve the field equation from the action and everything, and we get a metric that has as parameters alpha and the magnetic charge Qn. After that, we can perform an expansion of this metric function, and then we can match the parameters, and we can say that this generates this. So it's after you derive the metric coming from that, you match the parameters, and you say it generates this model.
Yes, yes. So the nonlinearity in electrodynamics, that's
here.
Yes, right. So the question. So okay. So what is the typical values of L, for example? They are constrained by the constraints from the nonlinear electrodynamics.
If we consider the black hole now, galaxy is like 10 to the power 10 or something.
10 to the power.
Which is huge, but compared to the radius of the black hole, it's like nothing. It's 10 to the 25 or something like that. I'm not entirely sure.
L is 10 to the 10 meters?
Yeah, 10 meters. I think it's in meters now.
Wait a second, but from flat space-time, do we have constraints?
Nonlinear electrodynamics, what they constraint is, I mean, the birefringence, not birefringence, but, there are a lot of effects which are measured from nonlinear electrodynamics.
Sure, I prefer to see this way of generating the geometry as a fake way. I mean, we can't expect that this is an actual theory that derives regular geometries. This is a way that we can generate these geometries to study them in an effective way. I mean, if you actually believe that this is the actual theory that generates regular geometries, yeah, sure, you can study some effects and see what is happening, but I'm not entirely convinced that this is the correct theory to study.
Yeah, Arshad, I mean, this can't be the right theory anyways because it doesn't have a Maxwell limit in the weak field. So it's
one of them have, right?
Yeah, one of them you can, yeah, but again, I think it's still good to be true. And we've seen before that energy theories were not successful, and we had more fundamental theories that made predictions, so why not having the same thing here?
Okay. Thanks.
Thank you.